I'm guessing this works. So let me first begin by thanking the organizers for inviting me here to Florence. It's great to be back. The first time I was here, I was a young, naive, foolish science enthusiast, and now I am at least two of those things. So today I want to tell you a bit about something that you've heard about over the last few days, maybe, I don't know, days, at least definitely you've heard about it today, the concept of what a Narain theory actually is. And the goal of today will be basically to define what this is and generalize it to arbitrary signatures. And this sort of grew out of some sort of pandemic era collaborations. I particularly was interested in the mathematics of a bunch of these things, bunch of the topics that I will tell you about today. Whereas I had a few colleagues of mine who were interested in the physics of this, and that physics has to do with so-called ensemble averages, which was first studied, I think, over the last 5 years or so by Saj, Schenker, and Stanford, who showed that ensemble averages are sort of important for quantum gravity. And then following some work by Maloney and Witten and Avkam Ejedi and others, this was generalized to 3 dimensions. So today's goal will basically be about introducing a lot of these topics and generalizing them to, as I would say, arbitrary signatures. And I'm going to be a bit slow because A, I'm quite exhausted, and B, it'll be a Blackboard talk. So you have plenty of option to stop me for questions. So the agenda for today basically is to start off with some mathematical preliminaries. May I close this door if it's okay? It's a bit of a draft and I made a poor choice of clothing. So the agenda for today basically we started with the mathematical preliminaries, and this has to do with so-called integer lattices and quadratic forms. So once we've introduced these topics, we will talk about, in particular, theta functions of lattices. And once we have theta functions, we'll be moving on to so-called Narain theories. And these, in some sense, are lattice-valued vertex operator algebras. And I will tell you about what the standard canonical definition of these theories are and how we are generalizing them. And by the way, for those of you who worked on, like anomaly cancellation or invented anomaly cancellation string theory, you might ask why I'm trying to generalize this to a set of cases where I'm not guaranteed anything nice physically. So what's kind of interesting is that when you do generalize them, you see a lot of interesting mathematical structures that pop up, and I'm interested primarily in these structures. So I'm going to we'll be studying the standard ones and the generalized ones. And once we have these guys, we're going to study a particular ingredient which has to, which allows you to do the ensemble average. It's called a theorem by Siegel and André Weil. It's called the Siegel-Weil theorem. And it tells you that if you have indefinite theta functions associated to indefinite lattices, then the so-called average of these theta functions over a particular locally symmetric space is going to be a real analytic Eisenstein series. Okay? Sorry, was there a question or no? Okay. Okay, so that's going to be the point of today's agenda for today. So we're going to start off with some mathematical preliminaries. So let's start off with part 1, which is the mathematical preliminaries. Mathematical preliminaries. So we'll be talking mostly about quadratic forms. And for most of the talk, I'll be talking about the field R and the ring of integers Z. But pretty much everything I say, at least mathematically, carries on as long as I'm not in a field of characteristic 2, right? So let me first begin with the definition of what it means to be a quadratic form. definition of a quadratic form. Quadratic form. So quadratic form is a polynomial so it's a quadratic form over, let's call it some field K. Polynomial of degree 2. 2. Degree 2 in n variables such that q of x is q of x1 to xn equals sum over I j in 1 to n qij xi xj, and qij defines a matrix of n by n matrix over k. Okay, and we are also going to be interested in a particular distinction. It's not there on the title over here, but mostly we're talking about definite and indefinite quadratic forms. So basically, if the matrix Qij has only positive or negative eigenvalues, then we say that Q is definite, else it is indefinite. Okay, and we also have the notion of a positive quadratic form. The positive quadratic form is basically a positive quadratic form. So this is my definition, abbreviation for quadratic form now. A positive quadratic form is basically defined as Q of x greater than 0 for all x in some n. And similarly, it's a negative quadratic form if this is less than 0. And so what's kind of, we will also be making the assumption that Q is a symmetric, non-degenerate quadratic form. So symmetric meaning that Qij is Qji and non-degenerate in the canonical sense. Okay, so, and it's also helpful, it's also kind of helpful to think about Q as a freely generated module, or the Z module. That is, Q is map from M to Z, where M basically is Z to the N, such that Q of alpha x equals alpha square Q of x for all alpha in Z. Okay? So once we have this structure, you can kind of already see where we're heading towards, that there is a sort of way in which we can think of these quadratic forms as lattices, right? So because lattices by themselves, lattices are in fact freely generated Z modules. So you can think of quadratic forms and lattices as being interchangeable with each other in this setting. And it's often quite helpful to do this because you can think of the lattices as generating some sort of aspects of the moduli space of the theory, whereas quadratic form telling you about the algebraic structure of the theory. Okay? And what this also allows us to do is that it tells you that there exists a vector space of some dimension, let's call it P plus Q, because I want to build towards something that's indefinite, there's a vector space of dimension p plus q, which admits q as a quadratic norm. Okay, so good. So now, once we have all of this, we can start thinking about lattices per se. Let me first change gears a bit and talk about lattices now. So we think of lattices lambda pq. We're going to be thinking only about the case where lambda pq are integer lattices in z pq or pq. And these lattices are indefinite, meaning that p and q are both not zero. And we also will be, for convergence, for conditions of convergence, we will be imposing that p plus q is greater than 4. This will come about later, but you can think about this already for the time being. And it's a known fact that every lattice of this form has an orthonormal basis. It's one of the, you can go read any book on quadratic forms of lattices, and this theorem will be proven in one of the very first few pages. Okay, and now that we have the notion of a lattice, we want to introduce the notion of norms on a lattice. So you can think of a vector v in a lattice lambda pq, and then the norm of a vector v is basically defined as n of v, which is sum over I equals 1 to p vi square plus, minus sum over I equals p plus 1 to p plus q vi square, right? So this is going to be the notion of norm of a vector in a lattice. And you can already see that this is a sort of diagonalized quadratic form. Diagonalized quadratic form. Okay, good. This means that I can take V multiplied by some matrix lambda times V, where lambda is basically just plus an antimatrix, which is a p times p antimatrix, and minus an antimatrix of q. So I have this block form of a quadratic form here. So now I say that if for all v in lambda pq, norm of v is an even integer, then we say that lambda pq is an even lattice, an even integer lattice. Similarly, if we take same thing, if this is an odd integer, then we say that this is an odd lattice. Okay. So far, any questions? I'm just defining things. Okay. We also have to define two more things before we actually start going towards the interesting stuff, which is, Okay, good. There is an odd Niemeyer lattice in 24 dimensions. I don't explicitly have the definition on my head, but you can go look it up on Wikipedia. Or yes, and sorry, can you repeat the question? Uh-huh. Oh, sorry, you're right. Sorry. Yeah, sorry. Okay, good. Yeah, sorry. Maybe I should not have said this. You're right. Maybe I don't even need odd lattice for today, so I don't even know why I said that. Okay, good. Thank you for that. So I want to define two more things. The next thing is the notion of the level of a lattice. So let's take the level of a lattice. So the level of a lattice is the smallest integer. So actually, before I do that, I need to define the dual lattice. So the dual lattice. So we define lambda star PQ is a set of all W in, let's say, ZPQ, such that V transpose lambda W in Z for all V in lambda PQ. And then we have the notion of a level of a lattice. This is the smallest integer. Integer such that for all W in lambda star PQ, the norm of lambda star W is even. Okay? So, and we also finally have self-dual lattices. So self-dual lattices are lattices for which lambda star PQ equals lambda PQ. So there are many examples of this. So in the definite cases, you have the E8 lattice, the D16 lattice, so on and so forth. On the Leach lattice, if you were there in on the earlier weeks, like, yeah? Yes, sorry, n times W. So one integer n such that n times, sorry, you're right. Okay, good. And if you have, and basically the other thing is that it's a known fact or statement is that self-dual lattices require that P minus Q is 0 mod 8. Okay? Yeah, you need an even integer. Okay. Good. Okay, so now that we have that, we can move on to theta functions of lattices. So theta functions of definite lattices are sort of much simpler to work with. So these things are in some sense arithmetic functions which tell you about the number of vectors of a particular norm, let's say inside a lattice. So if I were to do this for, let's say, a definite lattice, I'm just going to think of theta function of a lambda, this function, sum over all the vectors v in lambda, e to the 2 pi I norm of the vector v 2 times tau. And this is basically a holomorphic modular form of weight. So if this is p comma 0, holomorphic modular form of weight p over 2 on gamma naught of level of the lattice. Okay. So for the case of indefinite theta functions, it's a bit more complicated. Indefinite lattice theta functions. So this is a bit more involved in definition. So, oops. And this is studied quite extensively by Vinieras, Kudla, Milson, and also Jens Funke might have talked about it. And also Sergey has worked on this quite a bit. But for the time being, I'm just going to define it as theta of PQ is defined as sum over all the vectors L inside a lattice lambda PQ, e to the 2 pi, e to the pi I tau norm of the vector L minus pi times, tau 1 minus pi tau 2. And there's the other notion of what we need over here is the majorant of norm of a vector of L. So what the majorant actually means is that if I have a norm which is defined as this guy, then the majorant is basically sum over I equals 1 to p vi square plus sum over I equals p plus 1 to p plus q of vi square. So just as a minus sign, you have the plus sign. So that gives the majorant, and that defines another sort of a quadratic form, and that enters the notion of an indefinite lattice. Okay? So when you have indefinite lattices, which, oops, oh, that was my special chalk. Okay. For this case, yes, I will. I mean, for today's talk, everything is going to be even. In fact, for everything I will say today, yeah, they're even. Okay, so we also have the notion of the discriminant of a lattice. Discriminant of a lattice lambda, which we'll define as d lambda, is basically just lambda star quotient by lambda. And it clearly is clear that it's sort of clear that if lambda is a self-dual lattice, then this is just trivial. Okay. So at this point, we are now ready to move on to the notion of a moduli space of a lattice, which is the geometric moduli space of indefinite lattices. And this is simply, I'm going to define it, I'm going to denote it by MPQ. It's not be assumed, so we're clear that this is lambda of dimension p plus q and signature p minus q is just this quotient O PQ Q over R OPR OQR. So this guy basically takes care of the rotations, external rotation, the rotations of vectors inside the lattice, and then you have to quotient out by discrete shifts. On the other side, it is O, P, Q, Z. So this is the geometric space of indefinite lattices. And this is, I'm going to write this as integer shifts. Okay, so now that we have this space, we want to start constructing theories that have lattices as such lattices as charge lattices, and those theories are your Narain theories. Okay. Okay, so now we are ready to move on to the physics part of the talk, which is the part 2 is Narain theories. How am I doing for time, by the way? Do I have? I still have about 40 minutes, right? Okay. Okay, so we have these Narain theories, and we first start off with the standard case of Narain theories. The standard case of Narain theories is when, in that case, you have P equals Q, which we will just call D. Okay, so in some sense, these theories have, or the space defines a space of toroidal conformal field theories, and a toroidal conformal field theory of central charge D comma D. So these, in some sense, we'll be talking mostly about toroidal conformal field theories of central charge D, and such that whose holomorphic and anti-holomorphic Isomorphic parts or algebras contain a U1 level 1 to power D affine Kac-Moody algebra. Okay, so that is what we mean by toroidal conformal field theories, and in fact this space will be the space of toroidal conformal field theories. Kac-Moody algebra. Okay, so now these Kac-Moody currents in fact generate conserved charges, which we will call P left and P right. Okay, so that's some notation that I'm going to fix right now. And it's sort of known, if you study the OPEs of such things, that these charges actually are vectors inside some integer lattice. So we'll basically be looking at cases where P left and P right are now elements of some integer lattice, right? So known via OPEs that P equals P left, P right is a vector in some integer lattice. Okay, so good. Let me just quickly recap if I'm on the right page. I am on the right page. Okay, good. So okay, so now that we have these sort of toroidal CFTs, you want to look at firstly the partition functions. And the partition functions of such standard theories, which I will just denote Z, D, D, is some function of tau bar, is 1 over eta of tau to the 2D times sum over all P equals P left, P right, and P is some element of a D by D lattice, Q to the PL square over 2, Q bar to the P R square over 2, where Q is just E to the 2 pi I tau. Okay, so this is something that should be very, very similar to everyone. This is just one of the simplest partition functions that you see in string theory. Okay, and this is going to be, in fact, a theta function of an indefinite lattice. Okay, and in fact, it's a result due to Nikolai, Taormina, and others from the 1980s, that if you give me a toroidal CFT of central charge C left, C right equals D comma D, then you can associate to it a unimodular lattice or self-dual lattice gamma D comma D and vice versa. Okay, and this sort of puts the moduli space of lattices that we wrote down earlier on the same footing as moduli spaces of toroidal conformal field theories. Okay, and what this also means is that you often see the notion that you're on a point on the moduli space. So let's clarify what this actually means. So firstly is that the moduli space of toroidal CFTs of central charge D comma D is the same as MDD. And the next thing is that when we say that we are at a point in moduli space, we are at a point in moduli space, point in moduli space. What this means is that there actually is some notion of moduli, which is determined by the metric and the B field of the torus, of the toroidal, of the tori that you're considering. So if you were to take gamma as, let's call this P left, P right, and they're both function of some moduli, which we'll call them the metric and the B field, which is basically given in terms of some integers winding in momentum plus I. This is a standard one which many of you have seen in string theory, Wj. And then the other one is going to be Ni minus half Gij plus Dij Wj. So it's going to be a tuple such that Ni and Wi are both in some d-dimensional lattice lambda. Okay, and that's an integer lattice. And then this G and B define a metric and a closed two form on TD, where TD basically is RD quotiented out by that lattice over there. So this sources for you a metric G and a closed two form that is closed, which is your B field. Okay, so this is the standard Narain moduli space that you talk about. So when you're in this moduli space and you pick out the lattice, you basically are picking out one of these. You're picking out a gamma, and then you therefore pick out the charges P left and P right. Okay, so that is what people refer to as a standard Narain moduli space. So everything that we did so far is for the case where P and Q are both equal. So what we want to do is for the case when P and Q are not equal to each other, right? And I also mentioned at some point that one of the conditions for unimodularity is that P minus Q should be a multiple of 8. So far we are not going to impose any of these conditions, right? I mean, we're going to leave it free and see what happens. Are there any questions so far? I raised that way too quickly. I'm so sorry. In case you were copying it, I'll give you my notes. I'm sorry, I was a bit absent-minded. You should yell at me, right? Feel free to yell at me. Okay, now it's too late. Can I erase this still? Okay. Sorry. Okay. So now we are about to move on to the case of a generalized Narain theory. And this generalized Narain theory basically is the same as before. Only thing is that we are not going to set P and Q are not equal to each other. So P and Q are arbitrary, but for the sake of convergence, I will set that P plus Q is greater than 4. And without loss of generality, I can assume that P is greater than Q. Okay, so what I want to do is that since I'm not considering any sort of condition on unimodularity, I have to worry about this guy, the discriminant group now. Okay, so I need to worry about the fact that this guy is not trivial anymore. Okay, so recall that d of lambda is defined as lambda star quotient lambda, and this is not trivial if lambda is not a unimodular lattice. And this is going to introduce a lot of subtleties in the way you're constructing these CFTs. I mean, well, not CFTs, but constructing these theories. Okay, so we have to worry in some sense about two different kind of things. We have to worry about continuous data and discrete data. And let's start off with the discrete part of it, which is just lambda PQ. So that's very simple. That's analogous to what we did last time. And we are worrying about the continuous part. The continuous data is now tricky. Okay, so to do this, we have to first revisit the majorant in some sense. Okay, so we're going to define this space HQ as a set of all GL2 matrices, GLPQ matrices, GLPQ matrices, or Z, such that HQ inverse, sorry, no, Q equals Q, okay? And so Q, sorry? Have I made a mistake over here? Probably you're right, it's transpose, the act by transposition, you're right. Okay, and yeah, you're right. And I have the dimension of the space, HQ, is just PQ. So Q again is the norm that is defined with respect to lattice. And what I now have to do is worry about diagonalizing these quadratic forms. So I have two kinds of forms now. I have Q and I have H. So Q is in some sense the part left, I mean, this is basically sum over I, vi square minus I equals 1 to P, sum over I equals P plus 1 to Q, vi square. Okay, so that's going to be this guy, and this can actually be expressed in terms of some P plus Q bind. So you can diagonalize this. So basically the idea is that you want to diagonalize the entire Q. So we can always choose a diagonal basis to do this. And similarly, this guy is going to be sum over I equals 1 to P vi square plus sum over I equals P plus 1 to P plus Q vi square. And the way you diagonalize this is basically to choose a P plus Q bind on some quadratic space of dimension P plus Q. And you can choose a P plus Q bind, which I will call cal E. And that is going to be P plus Q, P comma Q times cal. And this is just going to be ET E. Right? So if you were to choose this field bind and choose in such a way that diagonalizes a quadratic form, then the majorant automatically follows this way. Okay? So now that we have this, we want to talk about the generalized Narain lattice. So now we go to the generalized Narain lattice. So this one we will define as P lambda is defined as the set of all P left and P right as before, is this P plus Q bind E acting on a vector L on all elements of the lattice L, such that L in lambda PQ and H equals ET E, right? And this is an element of the space HQ that I wrote out earlier. So this will be the generalized Narain lattice. And you can also define a norm on P lambda, which is given by Q. Now let me again make sure I'm on the right page. Good. So the norm on P lambda is basically just Q, which is norm on P lambda is then PL square minus PR square. So if I were to think of this as P left, PL, and this is PR, so PL square and PR square, that just give me PL square minus PR square. And similarly, H would then be just PL square plus PR square in terms of charges. Okay, so then I can also define the dual lattice, P lambda star is defined as rho equals P left, P right. And this is going to be, again, the same P plus Q bind acting on some alpha, where alpha is now in the dual lattice, alpha star, PQ, and H as above, or here. Okay, so that gives me the notion of a dual Narain lattice. And it basically means that if I take a vector over here and take the norm of the vector, I mean, compute the inner product of that with something over here, it's going to give me an integer. Okay, so that basically is the constraint on integer lattices. So The one thing that we have additionally here is that we have a discriminant. So we have a discriminant. We have d lambda. So whatever you do with the dual lattice over there needs to get defined with respect to a discriminant. Okay, so we have p star lambda, and alpha is now going to label an element of the discriminant group for me. Alpha is an element of the discriminant group of the lattice for me. And this is basically going to be set of all as before, rho equals p left, p right, equals E, the field bind, p plus q bind acting on alpha, where alpha is again an element. Oh, sorry, this is not good. I've chosen wrong notation. This is terrible notation, sorry. Let me take this to be beta, beta in lambda star, pq, okay. H as before. And then finally, I have the notion that this alpha and beta are equivalent to each other in the discriminant group. Alpha and beta are equivalent in d lambda. Okay, that means you can relate them to each other by some GL transformation. And it is sort of important to remember that while this here was a lattice, this is not really a lattice. So this is very, very important to remember. This guy is not a lattice. So it's rather a subspace of the lattice that we defined over there that contains this information, these labels about the discriminant group. Okay, and good. So now that we have all of this, we basically, well, there are two approaches you can do. One is that you can start off and study just the partition function, study the OPEs of this theory and compute the, and define vertex operator algebras for this theory. Or you can, what you want to do right now is we want to study the partition functions of this theory. Because at the end of the day, what you want to do is we want to take the partition function for a generalized theory and compute the average of it over the moduli space of the theory. So there are two things that we have to consider. One is that we have to consider what the partition function of the theory is, and then we have to also define what the moduli space of the theory is. So which board should I raise? I'll probably start with that one. Okay, so now let's look at the partition functions of the generalized Narain theories. Partition functions. So exactly as before, the partition functions are going to be the theta functions of these lattices divided by some appropriate eta powers. Okay, so let me quickly again make sure that I'm on the right page. Yes, I am here. So the partition function, again, as before, is I'm going to define this as z lambda, and alpha is the element of the discriminant group right now. And this is going to be a function of tau bar, but it's also going to depend on what modulus. This M is a shorthand for choosing PL and PR with an appropriate choice of metric and B field. Well, let me not say the metric and B field. It's an appropriate choice of P left and P right. And this is basically going to be the theta function of this lattice of tau bar M divided by eta of tau to the P eta bar of tau bar to the Q. Okay, so that is going to be the partition function of this. So M basically, I'll come to it in just a bit, but I probably erased it. Okay, let me backtrack. So we see M is basically, in some sense, this double here, P left and P right. And this P left and P right can be thought of as, they should be thought of as some integer. So maybe let me go back over here. So this P left and P right should be thought of as basically containing two different kinds of data. So the first part of the data comes from just integer lattices, that is the winding and the momentum. And then you have the actual data coming from the torus or whatever the target space of this theory is. So that part is basically going to give me a metric and a B field, right? There's going to be a two form inside of that and a metric. So all that together gets encoded in P left and P right. That is winding, momentum, G, and B. And that is basically what I refer to as M. Okay. This is a definition. Yes, there's a VA associated to this, and we actually defined it in our paper, but I'm not going to talk about it today. Okay, so good. Any more questions? Okay. So then this guy, theta, lambda, alpha, tau, tau bar, m, is then defined as some. By the way, a lot of these things are, I should also mention that a lot of these things, with respect to the theta functions of such lattices, were actually studied by Siegel about 100 years ago. And when you work through his TIFR lectures on quadratic forms, he writes it in a very convoluted way, but all these things are sort of explained in a way in which you can pull all these things out, right? So, yeah. So this guy is defined as sum over L in lambda plus a shift by the element of discriminant group, where alpha is now in the discriminant group of lambda. And then I will talk about as e to the pi I. Let me talk about this as p L square tau over 2 minus I pi tau bar p r square. No, that's not right. So let me actually let me define new notation, q left and q right, where q left is q plus h over 2, q right is h minus q over 2. And this guy defines for me the theta function of the lattice, and then I divide by appropriate eta powers. Okay? And so what this basically means is that if I take the theta function, I don't have a single theta function. In fact, I have order of the discriminant group lattice number of theta functions that I actually have to consider. So in some sense, everything is vector valued at this point. Okay? So now what you want to look at are the modular transformation properties of these theta functions. Yeah, you need a specific. You need to choose specific discriminant lattice, discriminant, and then you get a very specific partition function. But we want to deal with the averaging, so we can take all of this together. Yes, that's right. I'll show you. Sorry? What? No, H is the major end. So H is basically this guy, right? I fix the P plus Q bind on my, yeah, I fix that one. And once I fix that, this guy becomes locked in. Sorry? But no, if I'm in the moduli space, that gets, no, it, H does not, that's right, that's right. Yeah, yeah, exactly. So let me back up a quick second. Let me back up. Maybe Daniel, can you read your question again? No, there's no H dependent. It comes to the moduli. Yeah, so once I fix how to define H, there's no ambiguity in the definition of H. I hope I'm erasing the right board, so if I'm not, please yell at me. Okay, so finally I want to look at the modular transformations of this modular transformations. So I can look at, let's say, for example, the T transformation and the S transformation. So the T transformation, once I fix the lattice lambda and an element discriminant group, so if I said this tau goes to tau plus 1 with some moduli m, and basically this guy is e to the I pi q acting on alpha, there's a quadratic form acting on the element of the discriminant group, times v lambda alpha tau m. But the S transform is a bit more complicated. V lambda alpha minus 1 over tau m is 1 over det q square root e to the minus I pi p minus q over 4 tau to the p over 2 tau bar to the q over 2 times, I'm going to write that over here, sum over elements of the discriminant group e to the minus 2 pi I q acting quadratic form with alpha and gamma times theta gamma tau m. Okay, so these would be the modular transformations that you can work out. So generically too, you can actually, how am I doing for time? I have 10 more minutes. So you can actually even write down a generic modular transformation for this by taking an arbitrary element of the modular matrix and looking at what the transformations would be like. But probably in the interest of not having time, I'll probably skip for that because we don't exactly need it. So what we want to do now is, now that we have the properties of theta functions, we want to ask how the partition function transforms. Which one am I erasing? Okay, this one. How the partition. Hmm? Yes, yes. It took us a lot of time to actually show this, but yeah, it is. Okay, so now we look at the T transformations of the, well, it's sort of straightforward to look at the S transformation, but the only thing that we have to keep in mind is that when you have the T transformation, because you have the etas over there, it picks up the Rademacher phi, the phases. And therefore, what you end up with when you do just the T transformation is that you'll end up with a phase factor, right? So if you do T of Z Narain, some weight lambda, and then it picks up e to the minus 2 pi I p minus q over 24. So that comes from the Rademacher phi of the Dedekind eta functions, and the rest of it is same. E to the I pi q alpha, same thing as before. It just gives me z. Z alpha lambda. So that's the only thing one has to keep. That's the only subtlety, that when you do it for the full partition function on the T transformations, you have to keep in mind that the Rademacher phi enters when you do the modular transformation of the eta function. So now, finally, we have the moduli space. The moduli space of these generalized Narain theories. Okay, so the moduli space is the right part of it. I mean, the right coset of it is is analogous to the previous case, which is PQR, and then you have a quotient by OPR times OQR. So this still has the same role as it did before, in the sense that it rotates the different U1 charges among each other. But this part of the moduli space is going to be very different, because we want this guy. This is physically what's going to give you the T duality. This one is now also has the extra burden of preserving elements of the discriminant group, right? So this is very different. So I'm going to put a Q and then alpha over here, PQ. And this guy, OPQ, is defined as the set of all matrices in GL P comma Q over Z, such that sigma transpose Q sigma is Q, and then sigma alpha is the same as alpha in D of alpha. Okay, so it has to preserve the element of the discriminant group. That's the extra burden that the T-duality in such theories have to have. So once you have this guy, this is moduli space of PQ with a discriminant group alpha. Okay, or rather, we can also call it M lambda. Yes? Different choice. Yes. Yeah, yeah. So you have to preserve this. Sorry? Yeah, but this, I mean, this, I'm not saying this is one particular group, right? It can even be, sorry? Oh, locality. I haven't addressed the locality part just yet. Right, that's right. So I haven't moved on to that part just yet. So I'm still at the level where I'm dealing with, yeah, you're right. I haven't even, it's clearly not modular invariant. So, well, in this case, it's not modular invariant at all, right? So that's the thing. Like, unless you specify P minus Q is going to be 0 mod 8, I won't even have a chance of seeing modular invariance. So let me come back to your question in a bit. But now I want to quickly, in the last 4 minutes, move on to ensemble averages, if that's okay. Okay. So now, the ensemble average basic part is that I take these theta functions and I want to ask what comes out. Right? That is that I take okay, so firstly, it's a theorem of Siegel that this space still has a Haar measure endowed on it. M P Q alpha has a Haar measure endowed on it. And then the question now is, what happens when I construct the average of the theta function of lambda alpha, which is 1 over the volume of m lambda alpha, integrate over all m lambda alpha d mu theta lambda alpha tau m. And this basically, by virtue of the Siegel-Way theorem, is by virtue of the Siegel-Way theorem, this will be an Eisenstein series which has labels lambda alpha of tau, which is this delta alpha in lambda, which means that if this guy is an element of lambda, then it's going to be 0, 1, else it's going to be 0, plus sum over all integers that are co-prime to each other, c greater than 0, times some quadratic Gauss sum, which I will call gamma lambda cd over c tau plus d p over 2, c tau bar plus d q over 2, where this quadratic Gauss sum, gamma cd, is this quadratic Gauss sum, gamma alpha c d, the should make this capital G, Gauss sum is basically 1 over determinant of q power half e to the minus I pi p minus q over 4 minus c to the minus p plus q over 2 sum over LC in lambda c lambda e to the minus pi I d or c q of LC plus alpha. Okay, so this is the quadratic Gauss sum. Maybe just LC plus alpha. Let me just write it a bit bigger. E to the minus pi I d over c q of LC plus alpha. All right, so I'm preserving this guy even after the Siegel-Way theorem. And basically the idea then is that if you choose an element of the discriminant group, construct the theta function, and you average it over the full moduli space with a measure that Siegel gives you, you end up with this kind of a real analytic Eisenstein series, right? And then if you have to look at it, you have to look at all the values of alpha, then you'll get the full notion of your partition function. And you can also check that the modularity follows very analogously to the case of, it actually looks exactly the same as that of the theta functions. Now, only thing is that you don't have the M dependence anymore, okay? And in fact, this theorem can be, we've proven this theorem for both the for the indefinite case and also for the case when you actually consider orbifolds in theory. And in fact, there is quite a few things that we've done. One of the things is that we've considered orbifolds of these generalized Narain theories and still managed to construct all this machinery. And there are quite a few other things that one can do as well. You can also, in principle, construct not just theta functions over genus 1, depending on how you represent the quadratic form. You could take theta functions of higher genus, and then you can get things, for example, like Siegel theta functions at genus 2, and then you can do all this machinery all over again. So I don't know off the top of my head, so we haven't checked that yet. This will be modular invariant. What? So I have to divide this by eta, by the way. So only then it'll become modular invariant. Sorry, which gamma are you talking about? This guy. This is independent of tau. This is just the quadratic Gauss sum. Yeah. Yeah. It's everything. This is the word that I did not want to go into. You have to go into way representation work on the double cover of SL2Z to get all these things out. Okay, so I think this is a good place to stop and ask for more questions. So I'll stop here. Mm-hmm. Yes. It should be invariant on a congruent subgroup. So for that, you need the level of the lattice. So it'll be invariant on the gamma of the level of the lattice again, as I said. So you have to take you have alpha as the elements of the discriminant group, right? So you have to do no, alpha doesn't have weights. It doesn't. Yeah, it's a vector. Okay.
So can you make your statement precise? When you get, so what we need to do to get modular invariant?
So, firstly, Can I answer your question a bit later? I'm still trying to think about it. Okay. Yep.
No, I just looked at historically, when I was 4 years old, there was a paper called Indefinite Quadratic Pool.
Theta function. Yeah. So I have, in some sense, used that paper quite heavily to do everything that I've said today. But what is extra is how it's applied to lattice-valued Narain theories, basically. So that's new. The lattice-valued CFTs that I'm just defined over here, that's new. Yeah. So there are two versions of the paper. There's one in English and there's one in German. So I think the German one's a bit older. Yep. Yes, it'll have it's that's the other part which of course you don't get. They'll have some sort of notion of invariance of solid tori, 3D solid tori. So lens space invariance you can pull out of this gamma CDs basically. Exactly. You'll have a Chern-Simons theory of U1 to the P plus Q gauge group. And the alphas will label some other data, the Chern-Simons theory.
It's not possible to modify the definition of the Taylor space so that it's, I don't know, either alpha invariant with modular invariant.
Yeah, well, we've tried. I mean, we still have a lot of things that to think about in this because it's still quite new. So as of yet, I don't know the answer to this question. I mean, right, right. Why not what, sorry?
This group then is a subgroup of all your
Yes, that's right. Yeah, yeah, that's right.
that's a natural. And it's finite index.
That is right. That is right. Yeah, that's right. Yep. So you have to take all of these things. Yeah, that's right. So you have to take all of these things. So are there any more questions? I don't know. I mean, there are. You should ask Masahito this because even in our paper we have a very short speculative statement about what the holographic statements are. Yeah, I mean, I don't know. Yes. Mm-hmm. Right. Invariant or yes. So do you want it to be modular invariant or what's your okay. Right. Yes. Mm-hmm. Right. Right. Measure is modular invariant, yes. Sorry, which one are you talking about? I would do that.
Yeah, otherwise something doesn't work because
Okay. Maybe we should talk over the board because I'm not understanding. There's a communication error here. So let's talk again after this and then we can.